So today I want to do just a little bit on solid solution strengthening in aluminum and talk about some microstructure features. All right, and then just a reminder, next week I'm traveling, so we'll only have the recorded lectures, and those will be on commercially important specific aluminum alloys. When I get back, we'll have our sort of a review lecture just to go over and hit out all the main points to help you guys prepare for the exam coming up. All right, so strengthening mechanisms in aluminum alloys other than age hardening. Well, we've got solid solution strengthening, and really the details of that are all covered by and in our strengthening lecture. So really the idea is we want alloying elements that have a big difference in size and a large difference in elastic stiffness, right? Big difference in relative shear modulus with aluminum on the more compliant side, right? Gives us the best, right? And we talked about spherical and tetragonal distortions. So an FCC and HCP are close packed structures. A substitutional solute is going to be a relatively strong obstacle for an edge dislocation, a very weak for mixed if it has screw character, and because of the pure shear nature of the strain field, elastic strain field around a screw dislocation, there's only very limited interactions between a pure screw dislocation and the substitutional solid solution. The same goes for interstitial. In BCC, though, interstitials provide a big tetragonal distortion. It's not symmetric. So there's also a strong interaction with screw dislocations and edge dislocations in BCC. And we'll talk about this a lot with steels because this is the primary, one of the primary mechanisms. The carbon, interstitial carbon in iron gives you the properties of steel. All right. Just a reminder that for the FCC systems, the dislocations are rarely full dislocations. Most of the time they're partials, right? And partials will have a mixed character, right? And the increase in the pure shear component due to the shear strain due to the screw character means that at least one of the dislocations, the partials, will have a weak interaction. They can either both be weak or one can be strong and one can be weak, depending on the inclination of the Berger's vector with respect to the line direction, right? So it's impossible for them both to be pure edge character. So generally, when you dissociate into partials, you weaken your substitutional solid solution strengthening. In aluminum, where our stacking fault energy is high, our partials are not very far apart from each other, right? So they can still come together to be the pure screw parts to cross slip, right?
Yeah. Interstitial for FCC and HCP. So interstitial strain field is always tetragonal. Yeah.
But it's less distorted than in FCC than in BCC. We'll talk about specific interstitial sites in BCC when it's important, but just for now, right? We talked about cold working, right? And there's a number. The next couple slides I actually meant to copy into the cold working part this year and forgot because they're a little more relevant overall than just aluminum. But we have to consider a number of specific dislocation-dislocation interactions, right? When we talked about cold working, we really talked about it in terms of the average dislocation density for Taylor hardening, and we said that, yeah, dislocations interact, and they can form potent obstacles to other dislocations. Well, how do they do that? What are those mechanisms, right? And so I want to look at two particular cases. The first one is dislocation jog formation, right? So here we have a edge dislocation moving along this slip plane, and it comes into a screw dislocation that is aligned here. It's schematically shown as perfectly orthogonal, but if we think about the slip planes in FCC, it's never perfectly orthogonal. It's always at an inclination, right? Because our 1-1-1 planes are not normal to each other, right? They're at a different angle, right? So what do we call obstacle dislocations that lie oblique to a slip plane, that intersect a slip plane? Does anyone? These have a sort of a special name in the mechanics world, right? We call these forest dislocations. They're like trees that run through the slip plane, so they're called forest. To cut through them, you have to like cut down the forest, right? So imagine we have this edge dislocation here. It's moving this way in the plane, right? So what happens when these two dislocations intersect each other? Right? They're going to form a jog, right? So it will pass through. You can get it to pass through. Right? But look at our what happens to our Berger's vector stays the same, right? How do I know our Berger's vector has to stay the same? Right? Because this is a region between slipped and non-slipped region, so we have to maintain a constant Berger's vector. But if we look, where's my pointer? If you look at your notes, you can see our line direction has changed. So that means that this now is a segment that's lying on a different slip plane. Right? So it's not on the primary slip plane anymore. Right? So if we, in this case, it's still not an impediment to move because the relationship between this, so this is between an edge and a screw. So the jog on this edge isn't so much of an impediment, but if we contrast that with two screws that intersect, right, we have a very different case, right? What's different about the edge in the screw case? Right? Can this dislocation still move this way? Right? What's the Berger's vector? What's the direction of travel for an edge dislocation relative to its Berger's vector? Right? It's parallel. Right? So if we have this dislocation that's moving along this new slip plane, it's still moving in a direction possible to keep going in its original direction. Right? It's not a problem. But in the screw case, now we had a dislocation that was moving this way, and when we create the jog, this section here is moving on this slip plane in this direction, right? It can no longer keep moving in the forward direction. And so that means, how is this dislocation going to move now? Right? This can go here. So essentially, far away from this jog, this dislocation can keep moving forward. So it's going to form like a bend here. Right? Far away from the jog, this dislocation can keep moving forward. We're going to have a bend here, and this dislocation has to move sideways this way. So it's more like kink motion than regular dislocation. It's still different because we have sections that are moving on different slip planes. Right? Kinks are in the plane. Right? Jogs are change dislocation line length out of your slip plane. Right? So can you see that this is going to be very costly, a big impediment to move, because this jog can only go this way, and if this dislocation is already moved up, in order for this to move sideways, you have to pull this dislocation back. Right? So eventually your motion now becomes, I run this forward, my jog goes this way, and then it gives me more motion than I'm able to go forward here. Right? Yeah.
Jog.
This jog is edge character. Right? So the only way this jog can change planes, right? It can always climb in this slip plane. Right? But that's really slow. Right? So you guys talked about jogs and structures and defects, right? Dislocation, interaction, reactions. Well, I'll put up a little revision reading for you guys if you're a little confused. These slides are posted.
Well, they're not available.
What? I posted all of these.
I'm probably just
Ah! I'm sorry. I put them up last week. At least, it didn't even occur to me that you guys were not looking. Okay. Well, anyway, edge. I mean, you weren't writing things down. Edge jogs and a screw dislocation are real impediments to dislocation motion. All right. Does anyone know what we call a sessile dislocation that lies in the slip plane that you have to get around? Right. So here we have dislocation that cuts through the slip plane. We call those forest. If it lies in the slip plane that you're moving on and it's sessile, they just call it parallel dislocations. Right. And they give you two different parallel dislocations give rise to a backstress term. Forest dislocations give rise to work hardening. Okay. So the other interaction that we really want to consider in a little bit of detail is dipole formation. Right? And so, who here recalls what the stress field around an edge dislocation looks like? Is it homogeneous like a screw? If you write it in polar coordinates, right? It's not. It varies depending on what quadrant you're in, right? So if we have edge dislocations of opposite signs that come together like this, right? If they're on the same slip plane, what's going to happen? Right? They're just going to annihilate. Right? But if they're offset, all right, there's actually a minimum energy configuration where they have no net force on each other. And those happen to be when they're at a 45 degree, make a 45 degree angle. So when their coordinates make a nice right triangle here, right? You can look at this as the force between the dislocations by doing the Petch-Kohler calculation from the stress fields of the two edge dislocations. And you can see that to move them closer together, I have to apply a force. And to move them farther apart, there's a negative force pulling them back together. So this is a stable zero force configuration. And to get them away from each other, I have to do work, right? So this, right, you can imagine now we have two sources on two different slip planes, and they're pumping out dislocation loops, right? These loops are going to find a minima, and to pump out another loop, I'm going to have to drive these dislocations past each other, right? Right? And they're going to find a stable configuration. If I drive it past the first one, it's going to go to the second. And then if I drive it eventually so it passes the source, now I've got same sign dislocation. So I have a different interaction there, right? Right? And so this is, has everyone heard the term dislocation dipole? Okay. Well, if you haven't, that's what it means, right? We've got dislocations of opposite signs on different slip planes in an energetically stable configuration. Okay. So grain boundary strengthening, right? Review our notes on the Hall patch, but specifically for aluminum, we have to remember that the Hall patch slope for FCC is much lower than BCC or HCP, right? So what that means is we don't need to worry. In a lot of FCC systems, we can almost completely ignore the Hall patch effect, right? But aluminum's interesting. Aluminum, we can refine the grains very, very small and keep them more stable than we can in other FCC systems, right? So the Hall patch slope is low, but if we can get the grains really, really small, we can still have a significant Hall patch effect, right? So we want to use recrystallization, either dynamic recrystallization or recrystallization of a cold worked and then annealed product. And dynamic recrystallization is really interesting in aluminum because it doesn't recrystallize by nucleation and growth. It recrystallizes by what's called continuous recrystallization. So you have to have severe plastic deformation that rotates all the subgrains until they form a high angle grain boundary, right? But because of the high stacking fault energy, we never build up enough stored dislocation content to undergo a traditional nucleation and growth for dynamic, right? It recovers too easily. So it's a different mechanism. It's not super important for this, but we need to keep the grain size refined, right? So it doesn't do any good if we can make a small grain size by severe plastic deformation and then have the grains just grow as soon as we anneal it, right? We want to keep the grain size small. How do we keep the grain size small? Right? It was one of my rules of thumb, right? Grain boundary pinning, right? Right? We want to have secondary phases that are going to import a drag on the growing grain boundary, right? So what we want is a dispersion of particles that interact with a moving boundary that exerts a force. So if we want this to happen, what do we need, right? We need a strong interaction between the particle and the grain boundary, right? So when is this going to occur? we want the interfacial energy between the particle and the matrix to be lower than the grain boundary energy. Right? If I have a high energy grain boundary, and now I connect it with a particle, and that particle, the interfacial energy is lower than the grain boundary energy. I've now lowered the energy of my grain boundary, and I need to exert a force on it to make it move again. Right? So the second one, we also want to make sure that we don't introduce large particles at the grain boundary, right? Because these present problems, most likely because they're brittle and when they can fracture during the pile-up stresses will cause these particles to fracture. So really we want sub-micron particles so that we minimize this. Okay, so in aluminum, we always have, remember at the beginning I said a lot of elements and their impures, when they exist as impurities, come out as intermetallics, right? So titanium, chromium, nickel, iron, right? These will form intermetallic compounds that have small values of interfacial energies and are very effective grain refiners in aluminum. And they will keep the grain size small. Yeah.
I have a question about grain refinement.
Okay.
So I've read that grain refinement is one of the ways to kind of circumvent the strength ductility paradox. I understand why the strength is increasing, but having a pinning particle at the grain boundary, how is that not detrimental?
Well, so remember grain boundaries, it's hard to pass dislocations through grain boundaries anyway, right? So really the pinning effect is just to keep the grain boundaries from growing. The ductility when you get very fine grains, it's because you get increased ductility because you delocalize your slip, right? When you have a big grain and you have a source, you can activate many, many dislocations on that same plane. When you have lots and lots of fine grains, one of the reasons is because now you're activating a whole bunch of different slip systems, right? That's one reason. There's a whole bunch of other reasons that become specific mechanism and temperature dependent reasons, right? But and it doesn't always work. Making something very fine grained doesn't always help you ductility wise either, right? It's really system dependent. So, right? Okay. So we mentioned texture before, right? But we have to consider it. Right, so grains rotate during deformation, and we can have either deformation textures or annealing textures. Right, deformation textures form as a result of grain rotation during our deformation, and some real common ones are rolling textures or extrusion textures. Each deformation mode that you gives a stable different orientation, and because our polycrystal is anisotropic plastically, or single crystals are anisotropic plastically, texturing can give rise to strengthening, but we also have recrystallization textures that can form. What's the most common recrystallization texture? And what's an aluminum recrystallization texture? tends to be, if you have really cold work aluminum and you anneal it, you get a cube, what's called cube texture. So all of your cube faces are parallel, and your grain boundaries are, you have a whole bunch, a sheet with a whole bunch of A crystallographic axes all aligned, right? And the grains are just rotated with respect to each other. And so this is just a review of how texture forms, right? And so that's just some overview of what strengthening mechanisms are going on other than the precipitation strengthening in aluminum alloys, right? But if we're interested in design, right, if we're trying to develop a processing route in combination with deciding what alloy we're going to use for a particular application, what we really want to be able to do is link things back to the microstructural features that control those properties, right? That is, the defining concept of material science, right? Is that microstructure controls property, processing controls microstructure, right? That is what our field is, at least in terms of non-single crystal electronic materials. Right. So the first level of microstructure that we want to deal with is these coarse intermetallic compounds. Right? So these, we're going to say, are in the range of 0.5 micron to 10 microns. They can form during solidification or subsequent processing, and the big ones are iron impurities and silicon impurities. Right? There's a lot of casting alloys that use silicon, but for a forged alloy, having silicon in it will kill you because you'll form intermetallics, right? And these can be either soluble, classified as soluble, or insoluble, right? So insoluble are going to stay there until you get them up above the melting temperature, right? Soluble has a solvus in the solid state. So that's what we mean by these. So particles tend to be aligned as stringers, right, in fabricated products after working. So how on earth do these stringers form? We'll talk about that in just a minute. So put your thinking caps on and think about it. How on earth would you get these well-aligned rows of intermetallics? Right? The next level of microstructure that's critical for design are these submicron dispersoids, we'll say, from 0.05 microns, so 50 nanometers to 500 nanometers, right? These intermetallic compounds typically forming from transition metals or other alloying, right? There tend to be big kind of nasty groups, aluminum 20, copper 2, manganese 3, right? Zirconium, aluminum 3. These have an effect that they retard recrystallization and grain growth. So these are the intermetallics that we want to give us good strengthening from grain refinement. And the next level are the very fine precipitates, right? These are formed during the early stages of age hardening, our GP zones and our early intermediate precipitates. And this is the basis of our high strength from precipitation hardening, right? So when we talk about precipitation strengthening, we're really talking about these fine precipitates, right? Coarse intermetallics and submicron dispersions, even though they are precipitates, they're not, when we say precipitation hardened, we're really talking about just the ones that are coming out during aging, right? Grain size and shape, it should be pretty clear, right? We talked about Hall-Petch effect, And you can imagine what happens to grains is if you roll them, right? If you have a rolled sheet, what happens to your grains? They're going to elongate, right? Does it make sense that a elongated grain might have different properties? Right? We're going to have anisotropy, so we're going to have potentially longer slip lengths on some slip planes than others, so we can have a Hall Petch intragranular Hall Petch effects, depending on which slip systems are active. Dislocation substructure, right? This is formed during the work operations. This is Taylor hardening, right? So we want to consider the effect of all of these on the property of our aluminum, right? So we'll break it up into essentially two groups. We have the alloys that respond to heat treatments, our age hardening alloys, right? And our goal is to get a finely dispersed particles at great strength. And the non-heat treatable alloys, right? So we want to exploit other strengthening mechanisms. And we want emphasis to be on low-cost approaches to strengthening. Coarse intermetallics tend not to have a big effect on strength. Why not? All right. Where could they generally grow? Grain boundaries, right? And also, if they occur at a low volume fraction, they're far apart. So it's easy for dislocations to get around them. Right? But they do decrease ductility because they're easy to crack. Once you have a crack in an intermetallic, now you have an internal void in your material. Right? So I asked to think about where the stringers come from. So if we work our alloys, we're going to align the grains. All right? Right? When we roll, imagine you've got a particle with precipitates at the grain boundary. Then when you roll them, they become long ellipsoids, right? And that's really where you have where these stringers develop, right? The stringer distance is like your grain width in your as rolled state. So you're looking at parallel layers of grain boundaries, right? So these tend to be very directional, right? So sometimes called mechanical fibering, they cause a big anisotropy in mechanical properties, right? So if we think about it, we have this longitudinal direction. Imagine if we're pulling parallel to these stringers, right? That's going to give us our greatest strength. It's going to be least in the transverse direction, because now we have a whole bunch of parallel plates of these intermetallics that I'm now pulling orthogonal to, right? So I can easily crack, and now I'm pulling parallel to crack faces, right? Which is okay, except I've got a whole layer of cracks, right? If I'm pulling longitudinally, I don't have a whole layer of. I have a strip of cracks. And if these are particles, right, and I pull this way, even if I crack all of these, I don't have a good path to grow these cracks. But if I'm pulling this way, right, and I now have cracks in these going this way, I don't have to grow these cracks very long before they meet up with each other. Right? So we have a big anisotropy effects in these, right? And so we can see the difference between 2014, right? So here we're not forming a lot of these, and we have a very low degree of anisotropy that develops. But if we look at with zinc in there, right? Aluminum copper mag is okay. If we add zinc, we suddenly get a higher degree of strengthening, but we get a greater anisotropy ratio that develops. Right? For yield stress, right? Now, if we look at elongation, it's a different story, right? We lose 50% of our elongation along the transverse direction. Here we lose 70% of our ultimate tensile strength or our ultimate ductility along the transverse direction, right? So we already said Hall-Petch effect, and the value of this is very low compared to steels, right? Again, because it's FCC. We do get some strengthening, and aluminum can tolerate fine grain sizes. So that means if we go from 300 micron grain size down to 3 micron, we get essentially 3 times the yield strength, right? If we could go even smaller to sub-micron grains, we can get a really big benefit, right? So, how are we doing time-wise? Oh, perfect. Yeah. Sure.
So this part is I've also heard a bit about dispersed.
When you get really small.
But this part extends to the
This is yeah, so this is 1 over, right? This is, yeah, be careful when you're looking at this, right? This is 1 over the square root d, right? So these are small grains. Okay, you had another question? I thought I saw another hand up. Okay, so recovery and recrystallization in aluminum alloys. If we have very pure aluminum, recovery and recrystallization can occur at room temperature and below. So, anyone heard of a guy by the name of Carl Necker? He was a really good physical metallurgist. He worked at Los Alamos National Labs. He did a lot of important work on recovery and recrystallization and aluminum and copper. And so he did a bunch of tests on the East Coast at Drexel University and decided to drive back to Los Alamos. And this was in the 70s before cars had air conditioning. And by the time, after driving through the desert, by the time he got back to the lab, all of his samples were completely recrystallized, and he had gigantic grains, and all of his experiments were washed out, and he had to go redo them all again. Okay, so strain hardening, right? Because aluminum recovers really well, right? So why does aluminum recover really well? It's like one of the drums I've been beating the whole time. high stacking fault energy, partials close together, easy cross slip, dislocations can annihilate, right, through recovery mechanisms. Right? We can get around obstacles. Right? So we don't, strain hardening by cold working is not effective. Right? But as we decrease our purity, we can reduce this recovery and grain growth, recovery and recrystallization and grain growth can become inhibited due to solute drag effects. Right? So I realized something I said may have been confusing. I just said a couple slides back, aluminum doesn't dynamically recrystallize very easily. It doesn't recrystallize by nucleation and growth. It does this continuous, but it does statically recrystallize very, very easily, right? So remember the difference. Dynamic recrystallization is recrystallization you get during your test, right? So if I'm doing a compression test, right, I would be squishing my sample and my grains would be being refined, nucleating and growing new grains during the test, right? The grain structure that you get from linear friction welding or friction stir welding, right, completely dynamically recrystallized. Static recrystallization is you put in a bunch of cold work and then you heat it up and you get new grains that nucleate and grow, right? So aluminum does that very easily, but it does not dynamically recrystallize because recovery is too easy. Right? So the takeaway here is if we have particles with iron, manganese, and silicon, these impurities, we're going to get large solute drag effects. So small variations in purity can give us big differences in the microstructure and the properties of similarly processed alloys. Toughness is also a primary design criteria that we need to worry about. Right? So toughness. Right? So what do we think the microstructure features that control toughness are going to be? Is cracking in aluminum going to be ductile or brittle for the most part? Right? It's going to be ductile, right? But what if we have a whole bunch of big coarse intermetallic particles in the way, right? Essentially, we get things like this. We get crack paths that follow these large silicon intermetallic particles, right? Then we have decohesion that happens at the interface of these particles, right? Remember, one of the key things that we talked about for what makes an effective grain boundary pinning particle is that the interfacial energy is lower than the grain boundary gain boundary. So that means that we have a very low interfacial energy, that makes a very nice crack path, right? Because the crack doesn't have to do much work to separate the matrix from the particle, right? So if we have these intermetallics with low interfacial energies, they basically become beautiful paths for cracks to move along, right? So we have to consider the distribution of particles that can crack, the resistance to cleavage and decohesion, local strain concentrations that are going to potentially accelerate void coalescence, right? And then grain size when cracking are these coalescences along the grain boundaries.